यस ये है गुरुकुल हमारा।
Hello students, I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Welcome to the class of Control System 1. In this video, we will discuss on how to solve the different examples of Nyquist plot. And this is the second lecture on the Nyquist plot. In the previous lecture, we have discussed on the frequency response, the advantages of the frequency response over the time response, and how to find out the Nyquist plot and the Nyquist stability criteria, and the most important is the concept of encirclement, enclosement, and the principle of argument. Now in this video we will discuss on the stability conditions using Nyquist criteria and examples of system without pole at origin and with pole at origin and the references. So first we have started with this frequency response. Now the frequency response of a linear time invariant system is independent on the amplitude and phase of the input test signal. The transfer function of the system can be obtained from the frequency response. The design and parameter adjustment of the closed loop system for specified closed loop performance can be easily carried out in the frequency domain than the time domain. Also, the effect of noise disturbance and the parameter variations in frequency domain can be easily visualized. The transient response of any first order or second order systems can be obtained from the frequency response using the Fourier integral. So, there is also some correlation between the time domain and frequency domain specifications. So, time domain specification performance of a linear system can be predicted by using the frequency domain specifications. Now, in frequency domain, instead of standard test signal, we have used the sinusoidal wave, and generally sinusoidal test signal is given by RT equal to A into sin omega t, where A is the amplitude of the system. Now the closed loop transfer function Cs by Rs can be defined as the ratio of Gs by 1 plus Gs into Hs, where this Gs is the forward path transfer function and Hs is the feedback path transfer function. Now the characteristic equation can be obtained as 1 plus JSHS equal to 0. Now if we consider that the n is the number of anti-clockwise encirclement, then n is equal to z minus p. Generally, n can take positive value if z is greater than p, or negative value if z is less than p, or 0 if p is equal to z. And z is the number of zeros of QS or Fs encircled by the contour, and p is the number of poles poles of QS or FS encircled by the contour C. And then according to the principle of argument which we have discussed in the previous video lecture, then according to principle of argument, the number of encirclement of the origin made by the contour n is equal to z minus p. Now, there will be three possible cases. First is n is equal to 0. So, if n is equal to 0, then p is equal to z. That implies the system is stable. That means the contour in the S-plane encircles as many poles as equal to as many zeros. And there are no poles of GSHS in the right hand side of the S-plane. And if there are poles on the right hand side in the S-plane, then the system is unstable. Next, we'll consider the clockwise encirclement, and in that case, the system will always unstable. And if we consider the anti-clockwise encirclement of -1 plus j0 point, then system is stable if the number of anti-clockwise encirclement is same as number of poles of GSHS in the right half of the S-plane. And if the number of anti-clockwise encirclement is not equal to the number of poles of right hand side of S-plane, then the system will be stable. So generally n will be taken as positive, and if z is greater than p, and n will be negative if z is less than p. So in clockwise direction, if the S-plane encircles more number of zeros, that is z is greater than p in clockwise direction, then the origin QS plane will encircle origin n times in the clockwise direction. And in other words, we can say that the contour in the S-plane encircle more number of zeros than the poles of the QS or FS plane in counterclockwise direction, then the corresponding locus will map in the QS plane, which will encircle the origin in n times in the counterclockwise or anti-clockwise direction. So let's take an example. By using the Nyquist criteria, we need to find out the closed loop stability of a given open loop system. So here the open loop system is given as GS equal to 2 into 1 minus S divided by S plus 2 into S plus 3. So here we have to determine whether the closed loop system is stable or not. Now the system has no pole at origin. So we will select the Nyquist contour like this one, the 3-section Nyquist contour, where the C1 section, the omega is varying from 0 to infinite, and C2 is a semicircular arc with infinite radius, and the C3 section is here omega is varying from -infinity to 0. That means this Nyquist contour is selecting the whole right hand side of the S-plane. So let's map the section 1. So for mapping of section 1, the frequency omega is varying from 0 to infinity, and we know that any point in this axis do not have any real part. So S is written as sigma plus j omega, where sigma is the real part and j omega is the imaginary part. Now real part of will be 0 for any point that is located on this line. So we will put S is equal to j omega, and when we will put S is equal to j omega, the mapping of this section into GS plane is become the polar plot of GS. So G of j omega equal to 2 into 1 minus j omega divided by j omega plus 2 into j omega plus 3. if we compare this with x plus iy, where x is the real part and y is the imaginary part, then modulus of that will be find out like root over of x square plus y square, and the phase angle between them is tan inverse y by x. Now, the term which is located at numerator, for this term the angle contribution will be positive, and for the denominator terms, for each term the angle contribution will be negative. So using that we can find out the magnitude of g of s or g of j omega, and that is equal to 2 into root over of real part square. So this one is the real part and imaginary part is omega. So root over of 1 square, that is equal to 1 plus omega square. And for the denominator, it will be root over of omega square plus 2 square, that is equal to 4. Root over of 4 plus omega square. And this one will be root over of omega square plus 9 or 9 plus omega square. So next is the phase angle. So to find out the phase angle, the angle contribution for this 2, that is the gain, is 0 or none. And for this one, 1 minus j omega, this is located at the numerator. So the angle contribution will be tan inverse minus of omega by 1. So it can be written as tan inverse minus of omega. Now the remaining two terms, those are minus of tan inverse omega divided by 2, and for the next one, that is the minus of tan inverse omega divided by 3. Now in the similar way of polar plot, we are varying the omega from 0 to infinite, and when omega is varying from 0, so at 0 the magnitude is finding out as 0.33, where the phase angle is 0 degree, and when the omega value is infinite, then the magnitude becomes 0 and the phase angle is minus 270 degree. So next we will draw the polar plot of the section C1. So this is the real axis and this one is the imaginary axis, and we will consider the clockwise direction, and in clockwise direction this angle is minus 90 over here, minus 180 here and minus 270 over here. So when omega is varying from 0, at omega equal to 0, the graph starts from the 0 degree line, and on the 0 degree line the magnitude is 0.33. So this one is the 0 degree line or the reference line, and the magnitude is taken as 0.33 over here. Now omega starts to increase, and when omega is equal to infinite, then the line will be minus 270 degree line. So this line is the minus 270 degree line, and the magnitude on this line is 0. So next we will join these 2 points, and this is the mapping of section 1, which starts from 0 degree line where the magnitude is 0.33, and then it will terminate to the minus 270 degree line where the magnitude is 0. So this one is the mapping of section 1. So it starts at 0 degree with magnitude 0.33 and meet the origin along minus 270 degree when omega is infinite. And for the next section is C2 section. So if we check here the C2 section, actually it is a semicircular arc with infinite radius, and here theta is varying from this line where the angle is 90 degree and this angle is minus 90 degree. So theta is varying from plus 90 to minus 90. So in case of mapping of C2, the C2 will varying, S is varying from limit r tends to infinite, r e to the power j theta. That means it is a semicircular arc of infinite radius, and theta is varying from plus pi by 2 to minus pi by 2 or plus 90 to minus 90. So if we put g of s, and where s is equal to r e to the power j theta, then we will find out that limit r tends to infinite, g of r e to the power j theta becomes 0 into e to the power minus j theta. So now this one is minus theta. So if theta is 90, minus theta is minus 90. If theta is minus 90, then minus theta is plus 90. So C2, the magnitude is always 0 and the theta is varying from minus 90 to plus 90. So here the C2 section is mapped into a semicircular arc of radius 0 at origin in the GH plane. So it is just the origin in GH plane. And for the next section C3, so if we go back to the previous slide, here we can see that in C3 omega is varying from minus infinite to 0. So actually C1 is varying from 0 to infinity and C3 is varying from minus infinity to 0. So we can say that the C1 and C3 are the mirror images. So for the mapping of section 3, as the omega is varying from minus infinity to 0, so the locus is just the mirror image of the section C1. So this is the mirror image of section C1 and this is the mapping of C3 in the GH plane. So next we are finding out the complete Nyquist plot, where this one the plot is starting from 0.33 this point, and then this is the section 1 mapping. For section 2 it is plotted at 0, and for the section 3 it is the mirror image of section 1. So this one is the complete Nyquist plot. Now to find out the stability of the Nyquist system using Nyquist plot, we need to find out the number of encirclement in the minus 1 plus j0 point, because we know that the characteristic equation is 1 plus GSHS equal to 0, and from that we can say that GSHS is equal to minus 1. So we can say that the number of encirclement of the origin is equal to the number of encirclement of minus 1 in GSHS plane. So it is very important to find out the number of encirclement at minus 1 plus j0. That means the contour in QS plane is identical to the contour in GSHS plane if we shift the origin from 0 to minus 1 plus j0 point. And hence the Nyquist plot is mapping of Nyquist contour C in the GHS plane and shifting of the origin 0 to minus 1 plus j0 point. So next we will consider the point of intersection on the real axis. That means we need to find out this point of intersection. So to find out the point of intersection, we will divide it into two parts. One is real part and another is j omega part. That means S is equal to sigma plus j omega, and we will divide the g of j omega into real part and imaginary part. And we know that any point which is lying on this axis, this real axis, for that the imaginary part will be 0. So we will equate the imaginary part with 0. So here gj omega is written as in real part plus imaginary part, and equating the imaginary part equal to 0, we are finding out the value of omega, that is equal to 3.3166. So now from this 0.33 omega was 0, and when it crossed this real axis, then the omega is 3.3166, and here at origin the omega is infinite. Now we are going to put this value of omega 3.3166 at the mod of gj omega, and after that we will get the mod of gj omega is equal to 0.4. Now this point is located to the left hand side of the S-plane, and as we are using the mod sign, that's why the value is become positive over here, but actually the point is located at negative upside, so it is minus 0.4. So the Nyquist point plot intersects this real axis at minus 0.4. So now minus 1 plus j0 point is not located within this. So minus 1 plus j0 is outside of this point. That means the number of encirclement at minus 1 plus j0 point is always 0 for this problem. Now we will consider that the number of poles at the right hand side, open loop poles. So for the, if we consider the clockwise encirclement, then n is equal to 0 and for the z is equal to n plus p, and as the p is equal to 0, so z becomes n plus p is equal to 0 and hence the system will be stable. One thing you have to keep in mind that if you consider the clockwise encirclement, then the z becomes n plus p, and otherwise the formula will be changed. N is equal to z minus p. So we will consider always the clockwise direction, and the formula n is equal to z minus p or z is equal to n plus p. So hence the system is stable. So let's take another example where the system has only one pole at the origin. So here also we need to find out the closed loop system stability from the given open loop system Gs equal to 5 by s into s plus 1 into s plus 2 by using the Nyquist criteria. So now here the pole at origin is located. So for this type of transfer function, we need to choose the contour like this C4 section, which is actually overtaking this position. So C1 is like the same, omega is varying from 0 to infinite. For C2, it is the infinite radius semicircular arc, and theta is varying from plus 90 to minus 90. When C3, here omega is varying from minus infinity to 0, and C4, for this one, this is a very small semicircular arc with radius epsilon tends to 0. So now let us map the section 1. Just like the previous example, for the section 1 we are going to plot the polar plot of section 1, and here g of j omega equal to 5 by j omega into j omega plus 2 into j omega plus 1. So the mod of the j omega becomes 5 by, for this j omega term, so it can be written as 0 plus j omega, and the magnitude becomes root over of 0 square plus omega square, which gives actually only omega. And the angle contribution for the single pole is minus 90 degree, because this is located at denominator, so it is minus and tan inverse y by x. So here imaginary part is omega and real part is 0. So tan inverse omega by 0 becomes tan inverse infinite, and tan inverse infinity means 90 degree. So the angle contribution for single pole is minus 90 degree. And if a square was present, that means there is double pole at origin, then for each pole will be minus 90 degree. So for two poles it will be minus 180 degree like this. So if here the power is 2, then it will be multiplied by 2. If the power is 3, then it will be multiplied by 3. So just like this, the angle contribution can be calculated. So for this transfer function 5 by j omega into j omega plus 2 into j omega plus 1, for this j omega term the angle contribution is minus 90 degree. There is no angle contribution for this 5 because it is a constant term, and only real part is there and j omega part is not there, so there is no angle contribution. So here the angle is 0, and for this term j omega plus 1, the tan inverse, the imaginary part is omega and real part is 1. So tan inverse omega by 1 or only omega, and for this one it is tan inverse omega by 2. Now here also we are varying the omega value from 0 to infinite, and when omega equal to 0, the magnitude becomes infinite and the phase angle is minus 90 degrees. Whereas when omega is infinite, then the magnitude is 0 and the phase angle is minus 270 degrees. So we will start to draw the mapping from the minus 90 degree line. So from this minus 90 degree line, the magnitude is infinite. That's why it is coming from this side, and then it will cross the minus 180 degree line, that is the real axis, and then the minus 270 degree, the magnitude becomes 0. So this one is the mapping of the C1 section. And next we will plot the C2 section. So for C2, here the r e to the power j theta and r is the infinite because the C2 section is it is a semicircular arc with infinite radius and theta is varying from plus 90 to minus 90. And now if we put this value, then instead of s, then we will get g of s is equal to, the magnitude is 0 and e to the power minus 3j theta. That's why I am calculating here minus of 3 theta. So if you put theta is equal to plus 90 and minus 90, because theta is varying from plus 90 to minus 90, so minus 3 theta becomes minus 270 degree and plus 270 degree. So C2 is mapped into a circular arc with radius 0, that means this origin point at origin in the GH plane. So mapping of section C2 is actually a circular arc of radius 0 and it has been mapped into the origin of the GH plane. Next is the mapping of section C3, and in section C3 the omega is varying from minus infinity to 0. That means this is the mirror image of section C1. So this is just the mirror image of section C1 and you have to check the arrow signal accordingly. And next is the C4 section. So the mapping of C4 section is S-plane is mapped into GS plane can be obtained by substituting F equal to epsilon e to the power j theta, where epsilon tends to 0. So if we put that, then it becomes infinite e to the power minus j theta. Now for the C4 section theta is varying from minus pi by 2 to plus pi by 2, because the direction of C2 and direction of C4 is opposite. If you look, then when theta is minus pi by 2, so GS becomes infinite, the magnitude is infinite and the angle is plus pi by 2. Whereas for plus pi by 2, the magnitude is infinite and it is minus pi by 2. So the C4 section will be mapped into a semicircular arc of infinite radius. So this radius is infinite radius and the angle is varying from, this is plus pi by 2 to minus pi by 2. So this is the mapping of section 4. Now if we add the mapping of each section, then we get the complete Nyquist plot like this. So here this one is for the section 1, section 2 has been mapped into the origin with circular arc of radius 0, C3 section has been mapped into the mirror image of C1 section, and finally C4 is the infinite radius semicircular arc and theta is varying from plus 90 to minus 90. So this one is the complete Nyquist plot. Next we need to find out the stability of the system, whether the system is stable or not. So to find out the stability of the system, we need to find out the point of intersection at this point with the minus 180 degree line or the real axis. So to find out the point of intersection, again we are dividing into two parts. One is the real part and imaginary part, and again we are equating the imaginary part with 0. So after equating the imaginary part equal to 0, omega becomes plus minus root 2, and we are taking the omega as plus root 2, and if we put this omega equal to root 2 in magnitude, then it becomes 0.833. Now this 0.833 is positive because we are taking the magnitude mod over here, but actually it is located in the left hand side, so it is minus 0.833 point. Now here also there is no encirclement at minus 1 plus j0 point, and when there is no encirclement at minus 1 plus j0 point, then n is equal to 0 and the pole at the right hand side for the open loop system is also 0. So z becomes n plus p, that is equal to 0, and the system is stable. So let us take another example. Here the system has pole at origin and we need to find out the closed loop system stability of the given open loop system Gs equal to 2 divided by S into 1 minus 2S. So here the 0 location is there is no 0 in the system and poles are located at S is equal to 0 and S is equal to plus half. That means one pole is in the positive half side, that is the right hand side of the S plane. One pole is there, so P is considered here 1. Now as this pole at origin is located, so we will consider the Nyquist contour like this 4 section, and for each section we are going to map in the same way. For C1 section, omega is varying from 0 to infinite, and for that g of SHS is equal to 2 by j omega into 1 minus 2 j omega, where angle is minus 90 degree, and for this minus of tan inverse 2 omega by 1. So it becomes plus of tan inverse 2 omega. Now if we need to find out the magnitude, then it becomes 2 divided by omega into root over of omega plus 4 omega square. Next we need to find out the phase angle. So omega is varying from 0 to infinite. I have taken 4 more points and magnitude becomes infinity to 0, whereas the phase angle is minus 90 degree to 0 degree. So in the previous cases, all the cases the angle was decreasing. That means in clockwise direction this is minus 90, then minus 180, then minus 270 like this. But here this angle is opposite. First the angle is minus 90 degree and then it becomes 0 degree. That means it will not go from this side to minus 360 degree line, rather it will go from this side to the 0 degree line. So this is the difference. And next is the mapping of section 2. In the same way, when we plot the mapping of section 2, we are going to put S equal to limit r tends to infinite, because the section 2 is the infinite radius semicircular arc and r e to the power j theta in js, whereas the theta is varying from plus 90 to minus 90 in clockwise direction, and C2 is mapped into a circular arc with radius 0 in the origin of the GH plane. Next is the mapping of section C3, and when we are mapping the section C3, that is omega is varying from minus infinity to 0 and the locus is the mirror image of the section C1. So this is just the mirror image of section C1, but the arrowhead is the opposite. Now for the section C4, it is the semicircular arc of very small radius and epsilon tends to 0, and if we put epsilon tends to 0 and theta is varying from minus 90 degree to plus 90 degree, then it will be plotted into a circular arc with infinite radius. If you put the values of S in case of g of j omega, g of S, then you will get the value is equal to infinite into e to the power minus j theta. So that's why it has been mapped into a circular arc with radius infinite. and this is the complete Nyquist plot, where this one is the mapping for section 1. Section 2 has been mapped into the origin, and this one is the section 3, that is the mirror image of the section 1, and finally this one is the section 4 mapping. So here also there is no encirclement of the -1 plus j0 point. So number of encirclement n is equal to 0. But here there is one open loop pole that is located in the right hand side of the S-plane. So if a pole is located at right hand side of the S-plane, then the p equal to 1 and z is equal to n plus p, which becomes 1, that means not is equal to 0. So the system is unstable. So in this way we can find out the stability of the system. So if a problem is there where there is number of encirclement is not is equal to 0 and n is equal to 1, and if the number of poles is equal to -1, then only both will be cancelled out and it will be 0, but p cannot be -1. So the system will be unstable. So according to the number of encirclement and the number of poles, we can find out the stability of the system. And if there is no poles at right hand side or open loop poles, then p becomes 0, and there is no encirclement at the Nyquist plot and -1 plus j0, then n also becomes 0, and there will be z is equal to n plus p, which gives z is equal to 0. So the closed loop systems become stable. So using this method, we can easily find out whether the given system is stable or not by using the Nyquist criteria. These are the references. You can also follow the OCW that has been uploaded in the departmental website and college website. Thank you.